Okay, so let's continue with X-ray diffraction. This is our 5th lecture during that semester. During last 4 chapters, we have seen history of X-rays. We have seen X-ray sources, conventional X-ray sources rotating on a tube, and also cyclotron, synchrotrons, and free electron lasers. We have seen all of the X-ray sources, even old ones. And we have discussed X-ray matter interaction. We have seen absorption and scattering mechanisms. And what was the last chapter? The last chapter was concerning X-ray detectors. Right? We have seen gas ionization chambers, photographic films, proportional counters, what else? Semiconducting detectors and CCD counters. We have seen the details of all of that X-ray detectors. And now today we will continue with X-ray diffraction. So what is X-ray diffraction and when it was discovered? In 1912, von Laue proposed 2 conditions. If crystals in materials, if the crystals are formed from periodically arranged atoms, in addition to that, if the X-rays are electromagnetic waves with the wavelength of 5 angstrom, like the distance between the atoms within the crystals, then X-rays can be diffracted from the materials, from the crystals. So 2 proposals, okay, proposed by von Laue in 1912. So von Laue theoretically proposed this. Crystals are formed from periodically arranged atoms, and if the X-rays are electromagnetic waves with the wavelength close to the distance between the atoms, then X-rays can be diffracted from the crystals. This was the proposal. Then he was awarded by a Nobel Prize just 2 years after his proposal in 1914, Nobel Prize in Physics. Just after the proposal of von Laue, Friedrich and Knipping did some experiments in order to test these proposals. So what they have done, they have used copper sulfide in a crystal and then put that crystal into the way of an X-ray beam, okay? And then they detected the diffracted beam by using photographic film. And they have seen some spots on the photographic film due to the diffraction of X-rays. And the theoretical proposal of von Laue was proven by the experiments done by Friedrich and Knipping. Let me draw the experiment here. Let's consider that here we have a crystal, copper sulfide. And here we have an X-ray source. You produce X-rays with some certain beam size. And here there is a photographic film. We have discussed the details of this type of detectors. They were widely used in the past in order to detect X-rays. Nowadays, they are not used, of course, for scientific purposes, just only for medical purposes. So they have observed that there are some spots on the photographic film due to the diffraction from the crystal. Then they provided a proof for the theory of von Laue. And after these experiments, scientists concluded that X-rays are electromagnetic waves, and the crystals are formed from atoms which are periodically arranged within the crystal. In addition to the von Laue, in 1912, Bragg used much better mathematical formulation in order to determine the diffraction conditions in crystals. And just after the von Laue got the Nobel Prize in 1914, Nobel Prize in Physics, and in 1915, Nobel Prize in Physics went to Bragg due to that discovery. So they have also done first crystal structure determination. They have determined the crystal structure of sodium chloride, potassium chloride, and also potassium iodide. This discovery in X-rays and also this discovery in X-rays are very important steps. After that discoveries, X-rays have been started to use in many different fields to determine the crystal structures of the materials. So now let's have a look what is the diffraction from the crystals, diffraction of X-rays from the crystals. Here we have a crystal, you see that? This is one atomic layer, this is another atomic layer within the crystal structure. Actually, here for the just schematic representation, we put some interval between the atoms, but in reality, the atoms are touching to each other within the crystal. Okay, this is just schematic representation. Here we have an X-ray source. Let's assume that. Let me choose a pen here again, and here we have an X-ray source, and X-rays are produced within the source, and they are coming to the crystal, and they are reflected, diffracted, scattered, absorbed within the crystal. Okay, all the absorptions and diffraction scattering mechanisms can be happened within the crystal. Of course, during the X-ray experiments, as I explained during the last lectures, we use high energetic X-rays. Here, for example, in X-ray diffraction experiments, usually the energy is more than 8 kilo-electron volt. For this reason, the interaction between the X-rays and matter is mainly dominated by elastic scattering. Okay, so we have discussed this one. But of course, there is also a very small amount of absorption during that experiment. So here we have detector. Detector is waiting there. Okay, so X-rays enters into the material and they are reflected with same angle. So, but this is ideal case. Just don't forget that there are also many other X-rays scattered everywhere, okay, in 4 pi. So we think that this incoming X-ray beam is monochromatic. What is the meaning of monochromatic? It means that we have a single wavelength, okay? And all X-rays are parallel to each other, okay? we send X-rays with some certain theta angle here. You can see that angle. And they are reflected with some certain theta angle. So then what happens in that condition? X-rays are scattered everywhere, okay? Let me show you this laser pointer here. X-rays are scattered everywhere. As I told you, both scattering and absorption mechanisms will happen here, but the scattering is dominant because we are using hard X-rays, high energetic X-rays during X-ray diffraction experiments. And in some direction, X-rays become in the same phase and then they reinforce each other. Okay, here we have some scattered X-rays. They are in the same direction and they reinforce each other. I will talk about what is the reinforcing each other. Then the diffracted beam, the term for the diffracted beam can be considered that many X-rays reinforce each other in certain direction. Okay, this is the diffracted beam. So then, in general, diffraction is a scattering event. Okay, don't forget this. Diffraction is a part of scattering. So very special case of the scattering. So then let's talk about constructive and destructive interference. We have talked here that reinforcement of the X-rays. So how it happens? It is related to the constructive interference and destructive interference. Here we have two X-rays, okay, with the wavelength of lambda and the amplitude A. Here we have another X-ray with the same wavelength and same amplitude, okay? So they produce a constructive interference. The wavelength does not change and they have doubled amplitude. So crests and troughs, okay, these points and these points reinforce each other. This is the reinforcement we have discussed during the last transparency. But if we have a difference between the wavelengths, between the X-rays like this, for example, here we have again same X-ray with the same wavelength and same amplitude. Here we have another X-ray with same wavelength and same amplitude, but they have a phase difference in between, okay? They have phase difference with lambda half, okay? Then what happens? This part of the X-ray is cancelled by this part. This part of the X-ray is cancelled by this part. This is cancelled by this one. So it goes. Finally, what we have nothing. Crests and troughs cancel each other. Then this is called as destructive interference. Constructive interference and destructive interference. In order to understand the X-ray diffraction mechanism, this information is very, very useful and important. So now let's try to use that information and then try to explain X-ray diffraction formula developed by Bragg. And don't forget that this formula awarded by Nobel Prize in Physics in 1915. So here we have another schematic representation of the crystal and incoming and scattered X-rays. So this is one atomic plane. This is another atomic plane within the crystal. And this D is the distance between the atomic planes, interplanar distance. And here we have incident X-ray beam. It comes with some certain theta angle with the surface. And it is reflected with some theta angle, same theta angle. If this is theta, by using the geometry, you can also find that this is also theta. If you take a line which is perpendicular to the incoming X-ray, then you can get theta here. By using the same method, you can also understand that this is also theta. Okay. So what do you see here? This X-ray and this X-ray are coming together until that point, okay? They are coming together until that point. And after that point, again, they continue together. But what happens within the material? Let's consider that this first X-ray is reflected or scattered from the surface, from the top atomic layer, and this is diffracted from the bottom, okay? But you see here that they come together until that point and they continue together after that point, but this guy has some more distance compared to this one, okay? And this distance is given by AB plus BC, okay? So how to calculate this AB plus BC, and what is the name of this one? This distance here and this one is called as path difference. Path difference, okay? Path difference between that X-ray and that X-ray. So this path difference, by using the geometry, you can calculate. This one is d times sinus theta here, okay? D sinus theta. Here we have another d sinus theta, and the total path difference is given by delta to the sinus theta. Is it okay? So we found the path difference. So in order to see a signal in the detector, so detector is waiting there. Okay, here we have a detector, and this was the X-ray source. So detector is waiting there. In order to see a signal in the detector, these two X-rays must reinforce each other, okay? Otherwise, you cannot see any signal within the detector. So in order to see a constructive interference of both X-rays within the detector, this path difference must be n times lambda. Do you have any question here? This part is very important to understand the mechanism. Okay, so let me repeat. We have two X-rays here. They are scattered from the crystal, which have periodically arranged atoms. And then here we have a detector. Detector is waiting for the X-rays. If the path difference between two X-rays is equal to n times lambda, we will have constructive interference here, like this one. Okay, then we will see a signal. So in order to see the diffracted beam in the detector, this path difference must be equal to n times lambda. So delta is path difference, and this delta must be equal to n times lambda. This goes to developed formula, which is also called as Bragg's law. 2d sinus theta is equal to n times lambda. Here d is the interplanar distance, and this theta is the angle between incident beam and sample surface or crystal surface. Sometimes this theta is also shown like this, and the angle between X-ray and surface normal. In some books or in some lectures, maybe you have learned like this, but this does not change the results. Okay, so here we have theta, and then this is the integer number, starts from 1 and goes with 1, 2, 3, okay? and lambda is the wavelength of the X-ray. So this is the Bragg's law, and it is discovered in 1912 by Bragg, awarded by Nobel Prize in 1915. Do you have any question here? Okay, then let me continue. If I take n lambda here and put this 2d here, and what you will get, n lambda over 2d will be equal to sinus theta. So what is the maximum value of sinus theta? The maximum value of sinus theta is 1. Then this expression must be lower than 1. So this n lambda is usually equal to 2d, okay? For the n, we usually choose 1 in order to ensure that condition. So now let's try to get same formula by using scattering vector and also reciprocal lattice vector. You know that information from the solid-state physics lectures. Here we have incoming X-ray or incoming photon, okay, incoming electromagnetic wave. This is the K initial, and then it is reflected with same angle. Just consider this is the K final, okay? So this K here is given by scattering vector. And how to calculate this K? This K initial, maybe you remember, is given by 2 pi over lambda. But what about its component along that direction? This has this component and also this component. Let's consider that this is the angle theta. Okay, so this component perpendicular to the crystal surface, let's say, is given by 2 pi over lambda sinus theta, okay, this perpendicular component. And this also has, this one has also another component along that direction, and K is given by 2 times 2 pi over lambda sinus theta due to that expression, and it gives us that formula for a scattering vector. And from the solid-state physics lectures, we know that the reciprocal lattice vector is given by 4 pi over d. This is the unit vector n here. Here we have subscript HKL. These are the Miller indices for the crystal surfaces. I will go into detail about this. So for the diffraction condition, we should have this scattering vector must be equal to the reciprocal lattice vector. If you put them here, instead of scattering vector, let me write 4 pi over lambda sinus theta and unit vector. And then for the reciprocal lattice vector, 2 pi over the HKL unit vector. So what we have to the sinus theta is equal to lambda. Again, we have Bragg condition. Okay, do we have any question here? If not, let me continue. So what about DHKL, interplanar distance? This interplanar distance can be calculated for cubic, tetragonal, orthorhombic, hexagonal, and other crystal structures, okay? So we mostly use cubic and tetragonals. Hexagonal is also used, okay? So what we have here in case of cubic structures, maybe you also know that form of the calculation of D like this, 1 over D square is equal to H square plus K square plus L square. These are the Miller indices over A square. This is the lattice parameter. Okay, so this is for the cubic crystals. If we have tetragonal crystals, now we have C. I will not give you information about the crystal structures in detail, but maybe it is better to remind you here that in cubic structures, we have lattice parameter A here in that direction, A here in that direction, and A here. But in case of tetragonal crystals, we have A here, and C here, okay? For this reason, here we have something else in tetragonal crystals. It is also the same in hexagonal crystals. We have much more different crystal structure in hexagonal crystals, okay? So this is called as A and this is C. So we have different type of calculation for the D. This must be done in the solid state physics courses. I will not go into detail, but maybe we should discuss the crystal families later on. Okay, so here I would like to talk about structure factor. So what is structure factor? Why it is useful? I will talk about this. Structure factor gives us information about the diffraction from the which surfaces of the crystals or which planes of the crystals. So normally, if you consider, for example, a cubic structure, let me draw here. Let's consider that here we have a cubic structure. Okay, we have different surfaces. So this surface is here is 1, 0, 0, let's say, okay? But here I can choose another surface like this. Let me show you. Here we have another surface, this one. Cuts both the X and Y axis. And the name of this surface is 1, 1, 0. Okay, so we have another surface. Let me also draw that one. And many other. So 1 point here, 1 point here, 1 point here. Who knows the name of that surface? 1, 1, 1. Okay, so let's consider that you are investigating a cubic structure, for example, iron or nickel. You would like to characterize that material by using X-ray diffraction method. So you should know this plane will give you any X-ray diffraction signal or not. You should know this plane will give you or not, okay? So this is predicted by using structure factor. You have already seen that topic within the solid-state physics courses, and you have calculated structure factor for different crystals. Here, I will just summarize it, okay? So sometimes, depending on the crystal type, cubic, FCC cubic, BCC cubic, or hexagonal, okay? Depending on the crystal structure, some planes within the crystal always give lambda half phase difference. So what is the meaning of lambda half phase difference? Lambda half phase difference produces a diffractive interference. So you cannot see any diffraction from some planes of the crystals. Okay, here let me go back. Here we have discussed constructive interference and destructive interference. If X-ray scatters from some planes of the crystals, they always produce a destructive interference like this due to the lambda half pass difference, okay? This is the mechanism here. And you can calculate it. They are already calculated for different crystals. And before you start for your experiment, you should know whether that plane will give you any diffracted signal or not. Otherwise, it will take so much time for to complete your experiment, or even after several hours, you will not see something, okay? Because you are looking for the wrong place within the crystal. So then, if there is no diffraction from the plane, this structure factor means that it is zero there in that point. So this is the importance of the structure factor. So again, in solid-state physics lectures, this structure factor is calculated and given for body-centered cubic and face-centered cubic structures. So for example, in body-centered cubic structures, can you give me any example for the body-centered cubic? So we have iron in periodic table. It is BCC, and we have nickel, which is FCC, okay? So in case of iron, both of them are cubic, but this is body-centered, this is face-centered. I will not go into detail what is body-centered, what is face-centered. If you have any question, I can go into detail. So if you are, for example, investigating iron crystal, you can only get diffracted signals from even HKL planes. For example, you can get signal from 200 plane. You can get signal from 222 plane because it gives us an even number, okay? So, but from 100 plane or 111 plane, or let's say 210 planes, you cannot get something if you are investigating iron by using X-ray diffraction, because algebraic sum of the HKL numbers gives even number in total. Then we have some certain structure factor, which is given by 2F. And in case of odd numbers, F is 0, okay? You cannot get any X-ray diffraction signal from the dead surface of the iron. So do you have any question here in that part? If not, let me continue. If you are investigating nickel, for example, nickel is FCC, we get structure factor, which is equal to 4F if HKL, all of them are even or all of them are odd, okay? Here, for example, we have 111, 200, 2 to 0, okay, then we get diffraction signal from the nickel from FCC crystals. But if we have mixed HKL numbers like this, odd, even, even, even, odd, even here, okay, so then the structure factor is 0. So this is the importance of structure factor. So if you don't know that information, so let's consider that you have a thin nickel layer on silicon substrate. This is silicon. And then you have nickel here. Let's say thickness is 10 nanometer. And you would like to investigate that nickel by using X-ray diffraction method. Okay. So if you are looking for that signal, or if you are looking for that signal, or if you are looking for that signal, you cannot see any signal from the X-ray diffraction because they are not allowed from that planes of the nickel, from that planes of the SCC crystals. You will always get constructive interference, okay, due to the lambda half path difference between the X-rays. So now let me continue. There are many different X-ray diffraction measurements methods. Here I will show you 3 of them, and next week we will see applications of X-ray diffraction. We will investigate a real X-ray diffraction result, and we will try to understand what it tells us. So here, there are different methods. First of all, let me show you Lau method. You remember the Lau, okay? We have started with the proposal of von Lau, who predicted X-ray diffraction from the crystals. So in Lau method, we use continuous spectrum. What was the meaning of continuous spectrum? Continuous spectrum means that X-ray source contains many wavelengths. It is not monochromatic X-ray source, okay? We have different wavelengths, and incoming angle is constant, theta is constant, so crystal is fixed, okay? And then here we have a photographic film. This is the experiment done by Friedrich and Nipping. So what we see here, depending on the X-ray diffraction condition, each wavelength within that X-ray source select different diffraction angle, okay? And then they go to the photographic film and they produce spots here. So this is called as Lau method. Do you have any question here?
Nasıl spot oldu, ben onu anlamadım.
Okay, let me explain. This, do you remember the working principle of that X-ray films, photographic films?
Nasıl yani, çalışma prensibi olarak? İnce film olarak?
No. Just consider that this is a photographic film, X-ray detector. Okay, so maybe you have mixed this name film. This film is not thin film. It is not the material. Material is here. This is the photographic film, X-ray detector. Okay. Instead of photographic film, you can also use a CCD camera, for example, here in Lau method. Okay. This is the X-ray detector, let's consider. Here in this case is photographic film. And our sample is located here, which is crystal. And here we have a non-monochromatic X-ray source. Then continuous spectrum. This X-ray source contains many wavelengths, okay? So when they interact with the crystal, each wavelength within the X-ray beam selects certain diffraction angle, okay, in order to ensure the Bragg condition. Let me write here. I think close your microphone because it gives us background sounds. But whenever you would like to ask question, you can open it again. So here, let me remind you, Bragg's law, 2d sinus theta is equal to n times lambda. Okay, so within that crystal, we have different d values depending on the HKL, depending on the planes of the crystal, we have different d values. Okay, here on the right side, within that X-ray source, which is not monochromatic, it provides continuous spectrum, many wavelengths. So each wavelength within that X-ray source selects a special planes which produce X-ray diffraction. Okay, then we get diffracted beams in certain points on the photographic film. Do we have question here in that point, Mergim?
No, that's okay now.
Okay. So now let me continue after cleaning the board. Okay, so this is one of the most common methods in X-ray diffraction, theta to theta measurement. So what is the theta to theta measurement? Let me draw first of all, and then I will continue. Here we have a sample. X-ray is coming with some certain theta angle, and it is diffracted with some certain theta angle. Detector is waiting here, and this is the X-ray source. So in theta to theta measurement, lambda is constant. Here we have a monochromatic X-ray source, fixed lambda, fixed wavelength, okay? Then we change the theta angle by manipulating the sample like this. So just consider that this is our sample. X-ray is coming and diffracted like this. So we change the theta angle like this, okay, in X-ray diffraction experiment. But during that type of experiment, but during the movement of the sample, the detector is waiting here, also moved simultaneously, okay? So detector is also moving. By ensuring that condition, theta is equal to 2 theta over 2, okay? So we should always ensure that condition during that measurements. So I mean, if you look at that picture, if you move the source in that direction, then you also move the position of the detector. Okay, they are moving simultaneously. So what is 2 theta? I think I have explained this one in the previous lectures, but let me remind you again, what is 2 theta? Let's consider that here we have a sample, and here we have an X-ray source, provide monochromatic X-ray, and it comes on the surface with some theta angle, and then reflected with same theta angle, and detector is waiting here. This theta here usually called as sample angle, okay? The angle between X-ray and sample surface. If you continue like this, but you will see that this is also theta, right? And here we have another theta. So this is 2 theta. So what is this 2 theta? The angle between incoming beam and reflected beam, okay, goes to detector. For this reason, this 2 theta is also called as detector angle. Okay, so theta 2 theta scan or theta 2 theta measurement here, also known as sample detector scan, something like this. So this is widely used in X-ray diffraction experiments, especially in thin films. You have to ensure that condition. So another type of measurement, just theta scan. In that case, we have again monochromatic X-ray source. Lambda is constant, and detector position is also constant. So like this, let me draw again. Here we have X-ray source, and it comes with some certain theta angle, and this is the reflection angle. Detector is waiting here. The position of the detector is fixed. Okay, so we just manipulate the sample. So we just change the theta angle like this. This is the sample, this is the X-ray beam, and this is the reflected beam. Detector is waiting here. The position of the detector is fixed, and sample is moving like this. This is also called as rocking scan, okay? Called as rocking scan. And this type of measurements gives us the inhomogeneity within the crystals, crystal structure. Very useful method. But I will not go into detail for now. We have finished with that transparency. So during the, I wanted to continue today, but you told me that you don't have time. Next week, I will continue with X-ray diffraction applications. I will present you a real measurement with X-ray diffraction, and then we will try to analyze it. Which peak, which signal comes from the substrate, which signal comes from the thin film, okay? And what the shape of the signal or shape of the data tells us, and how to analyze the data by using Bragg's law and by using the information of intensity, X-ray intensity read by detector. We will talk about all these things during the next lecture. Kendinize iyi bakın. Görüşmek üzere.
Teşekkürler, iyi
Sağlıcakla
günler.
kalın.
Teşekkürler.